The following program is brought to you by Caltech.
Good evening. I'm Maury Garib, Vice Provost for Research and also a Faculty of Engineering at Caltech. And I would like to welcome all of you to our second Watson lecture of this quarter. And before I introduce our speaker tonight, I would like to bring your attention to our next Watson lecture, which will be given by Professor Dennis Kochman, and is titled, Everyone Starts Small, How Metals Learn to Behave. So that would be on February 12th, of course. Okay, getting back to our lecture tonight. As you know, our speaker tonight is Professor Ali Hajimiri. He received his BS degree from Sharif University of Technology and his master and PhD degrees from Stanford University. He has been on the faculty of California Institute of Technology since 1998, where he is the Thomas Myers Professor of Electrical Engineering and Professor of Medical Engineering and Director of Microelectronics Lab. His research interests include integrated circuits and systems for applications in sensors, biomedical devices, photonics, and communication systems. And prior to becoming a professor at Caltech, he worked at Philips Semiconductors and Sun Microsystems and Bell Labs. And in 2004, he was selected to the World TR35 as top innovator list of that basically every year is announced by MIT. He is also a fellow of IEEE, Institute of Electrical and Electronics Engineers, and has served as distinguished lecturer for IEEE. He has 65 granted US patents and many more pending applications. And he has co-authored about 150 reviewed papers in top academic journals, as well as authored a book and co-authored 6 chapters of different books. And he has won many awards for best papers and basically in different fields of electronics. Ali actually co-founded Axiom Micro Devices, whose fully integrated CMOS PA has shipped close to 200 million units. Perhaps you have one of those in your smartphones right now. Well, on a personal note, I'm very proud that I've been part of a team that we lured Ali, instead of going to Stanford, to come to Caltech. And Ali is actually one of my heroes at Caltech because he really represents the true spirit of our faculty's entrepreneurial nature, not only in starting new businesses, but also in their approach to research. To give you an example, Ali spent a year recently. After becoming a full professor, usually we go take a big rest. He took a course, actually a 1-year course or training in biology, in order to equip himself with necessary knowledge to allow himself to analyze new and challenging medical problems. He actually took courses. He sat side by side by our undergraduate students and asked the instructors actually to correct and give him the same harsh time they give to every other students. And he was very keen on that one. And the time that he invested, believe me, spending a year just focusing away from your research and some new fields is not something that every Caltech faculty will do. So in that respect, it was a big investment for him. But the result has been amazing because as you will hear tonight, among everything else he has done, he's come up with ideas for new diagnostic devices that one day may actually detect cancer cells and other disease cells very easily by the patient themselves. With this introduction, I would like all of you to welcome Ali to give his lecture tonight. Thank you.
Well, good evening, everyone, and thank you very much for that very kind introduction, Maury. It's a pleasure to be here tonight and being able to talk to you about some of the work we've done and share some of the results with you. Tonight, the title of my talk is a strange title in the sense that it's not mathematically accurate, as probably everyone knows. And the spirit behind that, as well as some of the examples, will show that it's really a way of thinking about the whole being more than its parts. And really, that really goes back to the concept of holistic circuits, the way we will and I will give you several examples of that. But before I do that, I'd like to start with a little bit of a historical review of how we are where we are in terms of integrated circuits. So I'm going to spend the first 10 minutes, 10, 15 minutes going over the history. And the history of integrated circuits actually is intertwined with the history of computation and storage. And really, as you can see, basically, if you start from the very ancient times, the history of ancient computation starts way back, more than 100,000 years BC, with the computational tools, the most basic ones we have, which are our fingers. Of course, these fine specimens are a little bit younger than that, but in general, those are the tools, the most basic tools that we use. Now, going forward, basically, the next tool that made things possible and made an advance was really the ability to store and keep track of the actual computation and storing the results. For example, the one that you see here in the middle, top right, top middle, is basically a multiplication table made by Sumerians. And this is pretty old, actually. If you think about it, it's more than 4,700 years old. Abacus, another mechanical device, which is very useful. Then we went to storage on various forms of papers. Basically, papyrus here is another example of the methods of storage. And this is a remarkable papyrus in the sense that it has multiple mathematical theorems and problems that were used by the students to study. This one is much more recent, but I decided to include it because it was developed independently. It's a mechanism it's more of a record-keeping device. It's an Inca's quipo. And what it is really they use the knots here to keep track of the numbers. So the numbers here basically are stored in the location and the number of knots that they have on each one of these strings. And what this does basically is another device for storing mathematical information. Moving on to more recent times, what we really have is that we observe a transition from a mechanical to electrical. And this is an important transition. We're starting off with things like slide rule. This is a very useful device for making multiplications and divisions using logarithms. And this is a very useful thing in that sense. It was used up until the mid-40s and 50s. And even, I was curious, so I had one actually, just wanted to learn how it worked when I was younger. And then the other thing, this is actually a Babbage difference machine. Charles Babbage came up with the idea around 1840 time frame. And what it was, he never got to build the whole thing. It was a machine that basically calculated the value of polynomials by completely mechanical means, using completely mechanical. So he had the full design, but he had a disagreement with his machinist, and at the end, basically, the parts that he was demanding from him and the precision that he was demanding was not something that basically he could give him, and they had a dispute. So basically, it wasn't built up until more recent times based on his complete design. But it's purely mechanical. Then this is another device. Basically, you have a tabulating machine that was used in the census of 1890 with punch cards. And going forward, this is probably the first all-digital computer of our time, which was made with electrical relays. These electrical relays basically are mechanical devices that have electrical input and electrical output. So we are transitioning from mechanical to electrical. This was built around 1941 by Konrad Zuse. Z3 relay computer. And this ENIAC is the first one that was built, the full computer built with vacuum tubes. So it gets rid of the large mechanical movement of the devices. So looking at this is actually one of those interesting transitions that we see. And this is an interesting curve. This is an interesting calculation. I think it's based on the work of Ray Kurzweil. And basically what it shows is a plot of computations per second, how many calculations you can perform per second for $1,000, for $1,000. How many computations can you get? And this is basically a plot of that versus time. And you can see that you had to spend a lot of money for certain number of computations back then. And once you had the relays, it became faster, and the vacuum tubes made it faster. And you can even see a change in the slope. The transition even became faster, and this is the so-called Moore's law, of course, of going forward. So he calls it Moore's fifth paradigm. And these are the devices involved, basically going from mechanical to electromechanical to electrical, but using vacuum. And this is basically the way things were going till a more recent time, till a wonderful device was invented. Now, I'm sure everyone has heard the name of transistors. Probably almost everyone has heard it. And what that is really is a solid state device. It's a device that allows you to go from transition from a vacuum-based system or a system that's not completely solid to a solid state device. This device, in my opinion, was invented by Julius Lilienfeld in 1925-30 in a sequence of patents that he actually filed. And this is an example of the one that was filed in 1928 and was granted in 1933. And this describes a MOSFET. It's really a MOSFET, which is a similar device to what we use today. And the patent is pretty clearly written. It's very well written, and it describes the device really the way it is. But he never published an actual article showing this device to work. So there's a lot of question about whether or not he actually made one. Irrespective of that, the first transistor that was really demonstrated publicly is this device. And I took this picture when I was working at Bell Labs myself. And this was made by these three gentlemen, for which they won the Nobel Prize of 1956. And I would like to think that I would consider it one of the top 10 inventions of all time. But of course, I'm biased. So in that sense, it's an important device, irrespective. So moving on, the next step was obviously to try to include more and more have more and more integration. So the idea was to, now if you can make one of these devices, what if you can make multiple ones? What are the things that you need to do to put them all together? Now this was, the basic idea is not that far-fetched. I mean, it's something that you would think that, yes, of course, you want to put more and more of them on the same substrate, on the same piece of semiconductor. But the question is how. There were three fundamental problems, the way I would think about it. One was how to make them in parallel, which was done by a process which is akin to printing press. It's a parallel process, a batch process. The other thing is how to keep them separated, isolated from each other. Because if they start interfering with each other, then what you really get is not a collection of independent devices. They're all attached to each other, and they wouldn't work really the way you want them. And the third problem is how to connect them to each other, metallization. And these problems were solved by various people. Some of them were named, and some of them were given more credit than the others. But in general, this was basically one of the examples of early integrated circuits that were designed and built. So this was basically used, this is a NOR gate that was used for the Apollo spacecraft. So basically, for the Apollo project, this was used. And the entire size of this market, to give you a sense, in 1962 was about $4 million. And so that gives you a sense of how rapidly things have grown. Now, of course, once you put things on the same substrate, make them on one substrate, then the next question is that, what's the next step? What would you do if you could put more than one transistor on one substrate? If you have two, then the next step would be to put more, right? And that's basically Moore's law, to put more and more on the chip. So the question is, how far can we go? And what are the things we need to do? Really, to put more devices, to cram more devices on the same substrate, you have to make them smaller. That's one thing you need to do. And this is one of the reasons for the scaling concept. The scaling really is a process by which we are making the transistor smaller and smaller. And the main driver for this, although some people would like to think that was really integrating more and more, the main driver for this is something else that we'll talk about in a second, which was the speed, really. But now these are some examples of some of the commercially available devices today. So for some of the commercially devices today, these are pretty small, if you want to think about it. The channel width of a typical transistor today, which is like, you can see the cross-section here, this is about 70 atoms wide, and this is a commercially available device. It's not really something researchy that much. And more interestingly, the gate width of this thing is like 3 atoms wide, and atoms are small. I mean, I know that everyone knows that atoms are small, but atoms are really small. Believe me. So that was one of the things. But the other interesting thing is that if you want to make something faster, if you want to make something move faster, what do you do with it? Think about it. If you wanted to make something faster, more nimble, it has to be lighter and smaller. The speed of these transistors really is determined to the first order by the time it takes an electron to get from one end to the other end. If you want to make it faster, if you make it shorter, then it becomes faster. I mean, really first order, zeroth order way of thinking about it. And that was, I think, the main driver for scaling, which also had this byproduct of making it denser and being able to pack more and more stuff on the same chip. So now, where are we now? So this is an interesting plot. So let me tell you what this plot tells you. The x-axis is obviously the year. And the y-axis is the number of transistors on a single chip. And this is real data. So this is around the time I was born, which is close to where the first microprocessor was introduced. This is very close, within a year of my birth. And this first microprocessor, a wonderful device, Intel's 4004, had about 2,300 transistors on it. And we've gone up, and there's no stopping it. This part of Moore's law is not stopping. And I believe actually this is going to speed up. It's going to become a little bit steeper because the other parts are slowing down. This is the number of transistors we can put on a single chip. This is a single device. Now, to give you an idea, this is the 4004. And these are the relative sizes of these things are to the scale. So, and this one is the Intel Xeon Phi 64 cores. So this is the relative sizes. You can see that the size hasn't increased that much, which means that the transistors have become much, much smaller, much denser. Now, the interesting thing is that another kind of a point is that Xbox One, for example, you can go and buy one for $500. And the main chip on that device has 5 billion, with a B, transistors on it. And that's not the largest chip. We are getting very close to the 10 billion. And we keep going. We will keep going. So this is a very, very different kind of ballgame. Keep in mind, the number of transistors on these chips are comparable to the number of people on this planet, on one single chip. These are mega ultra cities we're building. And for this chip to work, every single one of those transistors have to work. Not a single one can fail. Just keep that in mind. Now, the other thing and this is basically, by the way, these things are not that big as they appear on the screen. So this is the relative size of that chip compared to a penny. So it's not that big. It's basically less than an inch on the side, about 2/3 of an inch. About 3/4 of an inch on the side. So moving on, the other thing that happens when we make things smaller is that they become faster. Now, this is a similar plot in terms of x-axis, but on the y-axis is the cutoff frequency, the maximum frequency at which you have gain out of a transistor, some sort of an amplification. And we'll talk about this briefly a little bit later. Now, this is also a logarithmic plot. You can see when you go one step up, you basically multiply it by a factor of 10. So the transistors have gone from this point to that point. So basically, their speed has increased by more than a factor of 1,000 in terms of how fast they can operate and where you can get gain. Now, this is the part that's kind of slowing down. You can see it. And that's because of the physics of the device. And this is the one that I believe will force the number part to go up. Because if you can't make them faster, use more of them. Essentially, that's the philosophy. But now, the other interesting thing is that when you do this, when we make these transistors faster by making them smaller, it didn't come exactly for free. The price we paid is that we went from bulky, muscular devices like this, which are discrete devices, of course, to very, very delicate, yet agile devices. So we made them very small, very fast, but they're puny. So the question is that if we have a situation where we have an unlimited number of transistors at our disposal, no limit, but they are very, very weak individually, what do you do with that? We have to change our mindset. And this is not such an unusual mindset in terms of people have thought about this mindset before. This is from, of course, the wonderful Wizard of Oz. And this is a drawing from the original edition. And what you see here is that you really have two different paradigms. The army of mice versus the big lion. We've gone from the lion to an army of mice. And the way you use an army of mice is very different from the way you use a lion. If you had a lion at your disposal, you would use it very differently. And there are things that an army of mice can do that the lion can never do. They can get places that the lion can never get. They can do different things at the same time. And that's what we mean by a holistic perspective of design, in the sense that we really have to use this large number in a very different way, utilizing different aspects of the physics of the device as well as the nature of the device itself. So how do we do that? Well, I'm going to give you several examples of this thing. And one of the examples, we are going to start with an example which is using the context of waves, electromagnetic waves. So we'll do a little bit of it, take a little detour on waves, and we'll come back to our actual devices and what we actually did. So let's go and talk about waves. Of course, waves, we are familiar with the waves. We've seen the water waves, you know, the ripples on the ponds and everything, and all of those things are very interesting to us. They have interesting behavior. And if you think about it, waves are our primary means of communication and sensing for mid and long range. The two primary modes of long and mid-range communication for humans is vision and hearing, which relies on electromagnetics and acoustic waves. So you're relying on waves every day. I mean, you are hearing and seeing me because of the waves. So the waves have an interesting set of properties, right? So one of the interesting properties of waves that's quite interesting, is quite remarkable, is coherence. So let's talk about coherence. What do we mean by coherence? Well, to talk about the concept of coherence, let me run an experiment with your help. I will need everyone's participation in this. So let's see how it works. So why don't we say the rows to the right of the auditorium. So let's do one thing first as a group. So let's everyone think about your favorite one-digit number and say it out loud on the count of 3. Okay? 2, 3. Okay, what was the number? No coherence, right? So now let's try something else. Let everyone on the count of 3 say my favorite number, 5. Okay? 1, 2, 3. That's coherence. All right? So what happens when you have two waves that are acting, basically are coherent, they're going together, up and down together, like the red one and the blue one? If they add, they give you something larger. But the interesting thing about this that has twice the amplitude is that it has 4 times the energy. So you get 4 times the energy. And if they were going exactly out of phase, they would give you almost nothing. So does it mean that 1 plus 1 is 4 in terms of energy? Or does it mean 1 plus 1 is 0 in this case? Well, it depends if they're adding coherently or anti-coherently or incoherently. This would be anti-coherent. Well, this is, of course, not 1 plus 1, 4. I mean, this is really, if you want to write it correctly mathematically, you have to write it this way, because the power and energy is proportional to the amplitude squared. But other than that, and these are mathematically correct, so there's nothing really, there's no need to go back and revisit our basic principles of mathematics. But the concept is that once you get these two to work coherently, you get more than the energy of each one. So what happens? Does it violate the conservation of energy? Do you get more energy out than you put in, and we don't have to worry about the world energy problems, and that solves everything? No, unfortunately not. So what is happening? What's happening is that you get more energy at some places, but you get less at some other places. So now imagine you have two sources to generate ripples on a pond or any kind of wave. And they're going like that. So they are going together. And what you see here is a simulation of what happens. So these are the two sources. And you can see that in this direction, you're generating, let's take going straight up, you're generating waves. So are you in this direction and that direction. But if you look, there are these two channels where you don't transmit much energy. So you get more energy in these directions and less energy in other directions. So the total energy that you get is constant, but you concentrate them in a certain area more than others. Now, why is that important? Because now, imagine that I could get the coherence, and basically I could get everyone to act that way with a larger number of sources. So what if I have more sources that are acting coherently, going together, helping each other? So this is with 8. Now, if you look at the simulation, you see that most of energy is going where? Going upward. And you don't send much energy in other directions. So essentially, when you are doing this, you're forming a beam. And the more sources you put here, the narrower this beam becomes. So I can actually send more and more energy to a narrower sliver of space. And I can create this wave that moves only in this direction, going vertically right now. Now, what is even more interesting is that now imagine that if when you were saying my favorite number, I wanted to hear all of you guys say the 5 at the same time. But if I'm standing on this side of the stage, now I will hear the voices of the people on the other side, on the far end, a little bit later than the people on this side, right? What if I got them to start a little bit earlier? So all of your voices would arrive at my location at the same time. Then you have created a beam. Not only you have created a beam, but you have also focused it in my direction. And that's what this simulation shows. Now you can see the one on the right is going a little bit earlier than the one on the left. And what it does, it has created a beam. Not only has it created a beam, but also has steered it to the left. So this is the basis for what we call the phased array. A system of multiple sources that individually can be small, but collectively can add up to a large signal power. And this is something that can be used to generate a lot of power, and not only generate it and focus it in one direction, but also steer it in different directions. So keeping that in mind, this is another way. You can also do that on the receiver. You don't have to just be the transmitter. Now, on the receiver side, if you think about it, let's say I'm interested in the signals arriving from a certain direction, right? Arriving in this direction. Now, if I adjust the delays correctly, I can add them all in phase and coherently. But now, if I actually go and try to look at something else, and let's say another waveform that arrives from a different angle, I can actually suppress it by adding them out of phase. And this way, what happens is that essentially you get a suppression of the things you don't want and amplification of the things you do want. So you can basically focus which way you're listening. Now, the good news is that we all own one of these, or at least a pair of them forming a phased array. This is probably the way, and this is the way that, you know, if you're at a cocktail party and you're kind of like pretending to politely listening to somebody, and you're really listening to the more juicy conversation going on the other side, you're really using your phased array. It's a two-element one, but it still works. And actually, if you calculate the dimensions for the acoustic waves and the center of the audible range, the numbers work out. So it's not that it's completely crazy. So, and you know, we were so excited about this. And this concept, by the way, is not a new concept. This concept has been around for a long time. But we were kind of like wanted to demonstrate it. So this is when we went out with some of the grad students, and they enjoyed it because they came out of their caves. And we went and had a field day. So basically, this is the wavefront. If you look at it here, we created a wavefront. The way we did it is that we gave each person a number, and we said 1, 2, 3, 4, 5, 6, 7, 8, and at the time of when your number was called, you basically created a wave. And you can see that you created a wave, in this case, that went to the left. So yeah, we were having fun with that, but that's a way to demonstrate something that's already known. So we did this with what kind of waves? With water waves, for example, or we talked about acoustic waves. But electromagnetic waves are also waves. And electromagnetic waves cover a broad range of the things that we interact with and deal with, right? I mean, if you think about it, this is the broad spectrum of the wave, electromagnetic wave. You start with long wavelengths, low frequencies, like this. These are radio frequencies that you use for, let's say, AM and FM radio. And then you go to microwave frequencies that you have on your microwave, and so your cellular phones are operating at those frequencies. Then you have this range in the middle, terahertz, that we'll talk a little bit more about. Infrared, visible. Light is electromagnetic wave. Ultraviolet, you go to X-ray, gamma ray, and all of the range. So they're all essentially the same thing at different frequencies with different wavelengths. So they're all waves at different frequencies. So, and this is an interesting part of the spectrum, which is pretty hard to generate. It has been very difficult to generate things in this range. This is a range of frequencies that's basically called the Terahertz Gap, between 0.3 terahertz to 3 terahertz. And there are many applications for it because this allows you to do fine resolution systems. You can use it for example, human-machine interface. You can use it for touchless gaming. Nowadays, we have systems like that, but they are not very accurate. This way, you can actually detect the movements of the eyelid and things of that sort. You can detect the eye movements. You can use it for very high-speed communication. You can use it for security imaging. You have such systems at airports today, but they're bulky and very expensive. The question is that can we make them very compact and cheap? And then you can use it obviously for medical imaging and applications. Now, the interesting thing about the terahertz radiation is that it being at a frequency where basically there's non-ionizing photon energy, and this is a more of a technical detail, they are safer. They cannot induce chemical change directly. And what they do, they can actually only warm things up. Now, if you warm things up, if you warm it enough, then you can induce chemical change through cooking them. But other than that, they don't intrinsically create chemical change, unlike things like X-ray. But the challenge, so this would be very useful. There are many applications for this, but this involves making things that operate above the cutoff frequency of the transistor. You remember the frequency plot that we were talking about early on? And let's talk about that cutoff frequency a little bit more, the idea of what is a cutoff frequency of a transistor. This is the symbol for the transistor, by the way. If you're not an electrical engineer, there is no need to know that, but of a MOSFET. And now if you have an input at a low frequency, a wave at a low frequency coming in, this transistor amplifies it, so it makes it larger, right? It makes it bigger. At frequencies below the cutoff frequency. Now, at the cutoff frequency, essentially what you get out is comparable to what you put in. And what this is really is that this is the definition of cutoff frequency, and above which frequency, when you go to very high frequencies, what you get out is smaller than what you put in. So one could argue that a piece of wire would be more useful than this transistor because it at least doesn't attenuate it. But it's a little bit more subtle than that. And the subtlety really is that, yes, you don't get gain, but there is still power. And this really goes back to the nonlinearity and a more technical detail of this thing. But what it is really is that the waveforms don't really look like the way I showed them, like pure sinusoid. And they look like this. And that means that there's energy at higher frequency. So the question is that can we come up with a way to harness this energy, take it out, and radiate it out? So we came up with this idea. Actually, my former student, Professor Kaushik Sengupta, he's a professor at Princeton now. And we actually focused on this, mostly Kaushik worked on this. And one of the things that we did was that essentially we created this structure, which we call the distributed active radiator. And what this really is a method of using the finite speed of light to create the right phases in the system by using a large number of transistors and devices to create a structure that radiates electromagnetically very efficiently. And it uses multiple transistors, multiple small transistors to combine power and generate it. Now, once you make one of these, you remember the concept of phased arrays. We had multiple sources, right? If you have multiple sources, then you can play all sorts of games by controlling the relative phases of these things. So now you can make an array of these things. And they will each radiate a certain amount, and if you combine them coherently, you can get all the benefits of beam forming and beam steering. And we made a chip like that, based on that. So this is basically a 4x4 array of these things. These are the individual radiators, the DARs, and this is the entire system. This is about 2.7 millimeters. To give you a sense, it's about 1/8 of an inch on the side. This is small. Now, it's that chip in the middle. It's that thing. So this is all the cast and crew supporting the prima donna here. And basically what it is, it just radiates directly out, and it forms this beam, and it can steer it. So does it work? Well, yeah, these are measurement results. And what these plots show is that you can form a beam, this blue curve, and you can steer it to the right and left, up and down. So you can go left and right, up and down, which basically is the basic things that you need to have for beam steering. And then we said, OK, well, if you have this, if you want to have a full system, you want to make a camera, a detector for this. So if you make multiple detectors, if you make an array of detectors on another chip, this is another chip, you can make a terahertz camera. Each one of these, you can think of it as a pixel. Well, now, this is not really a very high megapixel camera. This is like a 16-pixel camera at this point. But it's scalable. You can add more and more pixels and get it to a point where you can get higher resolution, right? And then we said, OK, can we image stuff with this? So we started imaging things. So these are real images of some of these things that we actually did. So this is an example of a key inside an envelope. We know that it goes through soft matter, so you can actually see it. This is a drill bit inside a plastic casing. So you can see through objects by looking at it. This is a pass for subway, I believe, from Atlanta. We were in Atlanta for a conference and then picked it up. And this one is the antenna. You can see the RFID chip, the antenna, everything inside it. This is a bag of sugar with sugar and no sugar. And then here are some other medical, kind of some more biological matters. Leaves, dry and fresh. And then you have chicken tissue. Different kinds of tissue will have different kind of absorption, fat, muscle, and if you have more, basically you have you can differentiate between bones, cartilage, muscle, and fat using this kind of terahertz imaging over very thin layers of matter. Now, and then we said, okay, well, if you put all of them together, can you make the entire system with a silicon thing? The point of making this in silicon chip using a CMOS technology is that these things in volume will cost very little. Because of that wonderful scaling that we have, because of that huge number of transistors that we can make, these things in volumes will cost less than $1. So you can think about putting them on your phone or other things, other applications. And that's a completely different question of like, what are the other things you can do? But there are many, many, many applications for something like that. And these are some actual images for the entire system. And this was something that we did as a demonstration of security imaging. So this is the object we imaged. And this is the image we got. And this is what's inside that object. All right. So here's the question. So the next, going forward. So that was an example. So we did make these phased arrays in very high frequencies. We've done it actually with RF frequencies, microwave frequencies, millimeter wave frequencies. But then the other frontier is that next frequency up, is light, visible or near visible light. The question is that, can we do this with light? Because if we could, we would be bending the light, right? Can we bend the light? So let's see. So the idea here is that if we want to make a system, a phased array again, but in optical frequencies, using silicon photonics chips. And the way it would work is that you feed it with a laser or multiple lasers, and then what it does, it forms a beam with that laser. And now what you can do is that you can electronically control, by controlling the delays, you can electronically control where this beam is pointing. Imagine my laser pointer, but now imagine that I could move it back and forth in different directions without any mechanical movement whatsoever. Nothing moves mechanically. And when things don't move mechanically, they become much faster if you deal with things that are moving electrically. So once you can do that, then possibly you could do a raster scanning. So we made one, actually, a postdoc and a student of mine, Behruz and Firuz, they actually made this. And this is the active part of it. So this is the picture of the die. This is the die photo. Again, this is about 1 millimeter on the side. This is very small. And this is the active part of it, which is even smaller. So it's a 4x4 array. It's a very small array. I mean, if you want to make a more focused, smaller, very sharp spot, you have to have a larger array. But we started with like a 4x416 as a proof of concept. And the spot size would not be super small, but it would be sufficient to demonstrate the concept. So you have that radius. And this is the actual chip as a part of the test board that we have there. And these things each radiate light. They couple the bright light out. And what happens is that in free space, they add either coherently in certain directions or incoherently in other directions. So we made this, and it does bend the light. What you can see is a demonstration. These are basically simulations of what it should do, and these are actually measurements. So you can see that we can form a spot, and we can move the spot left and right and up and down. So you can go in both directions. So you are literally do that. So we said, OK, well, if we can do this, can we form an image? Well, we said, OK, wait, why don't we start with something simple, like a triangle? And how do we form an image if you have a spot? Well, think about it. If I could move the spot very rapidly, with my hand, it's very difficult to make a triangle, right? Because my hand is a mechanical movement. But if I have an electrical movement, things become a lot easier. So we are going to go slow with the spot, and then make it go faster and faster and faster, and see how it performs. So look at the spot. This is a real measurement. And we are making our triangle. Then we thought, OK, maybe we can play a little bit of game. Happy faces, sad faces, things of that sort. So, well, let's see them. So in the beginning, you can't tell if it's doing anything. But once it goes fast enough, then you can see. There you go. All right? OK. And then we said, well, we are at California Institute of Technology. See if we can make the C, I, and T. And then we made them individually. We said, well, OK, why can't we just go through the sequence? And that's bending the light. All right. Changing subject. So the next thing is that, yes, we can make these systems that are very complex. But because they are made of things that are very small, and there's a very large number of them, the possibility of failure goes up. Once you basically think about it, if you put 10 million things of any things next to each other, the possibility of at least one of them failing is quite high. So to avoid that, you have to go through extreme measures to make sure that everything is perfect. But even in that case, things are become very expensive and very difficult, and there's a limit to how much you can do that. But now the question is that, do we really need to do that? Or can we make circuits in such a way that they can actually heal themselves? Well, our bodies do that, right? If you look at a wound, it heals over time. Why can't ICs do that? Can we make chips, ICs, that actually heal themselves? And well, we went about doing this, and I'm going to not go through all of the technical details. So this one doesn't mean anything to you probably if you're not an electrical engineer. And don't worry about it, it's not supposed to. So, but what it is that this is a demonstration. This was a platform. This is a particular amplifier. But what to take away from this is that this system has a lot of sensors and actuators. It has mechanisms of detecting failures of different kind and actuating things, changing things to make amends for that and correct them. Now, what this does is that eventually at the end of the day, it's a system, it has a brain in it, that basically tries to find the best it can make out of the cards it's dealt. So whatever it ends up with, it says, OK, well, these are the cards I'm dealt with. I have a good attitude. I'll try to make the best out of it, right? And if you do that, you have essentially created a self-healing system, because it does the best it can possibly do. And these are examples of how it performs. Now, as an example, this is the power consumption. Power consumption is very important when you make electronics, because that determines how long your batteries last. If you have your power consumption, you've doubled your battery life for a portable device. So one of the things it did is that when it self-healed, it reduced the power consumption significantly. So these are for 20 different chips, 20 different samples. We tried this system before healing. So we had a system such that we could operate without healing and say, well, OK, now go heal. And basically, when you ask it to heal, it made the power consumption substantially lower. And interesting enough, also, things became more similar to each other. It's kind of like that old adage from, I believe Balzac said, who said, all happy families are the same. So in a sense that, if they are operating close to optimum, they are very similar to each other. And you can see that these solid lines are basically much closer to each other than these dashed lines. And this is shown in this histogram. So what we have here is that then we said, OK, well, once you have something like that, it should be able to correct for heart failures, serious, destructive, catastrophic failures. So we have these high-power lasers in our lab that we can actually blast things on the chip and destroy different parts of the chip. So we said, OK, it was not intended for this. We said, what happens? Let's see what happens if you do this. So we started blasting the chip. So we started blasting different parts and important parts of the circuit and see what it does. And when we did that, it interestingly recovered. So what you see is basically that the red lines are after each blast, what it performed before healing, and the green and the blue lines are the ones that it did after two different ways of healing, which essentially resulted in more or less the same performance for the most part. So it recuperated. It basically reclaimed as much of the lost performance as it could. And it was substantial in many cases. So it basically can heal itself against those kind of damages. So we said, okay, well, these systems can be operating in these regimes. Then what are the other applications where we can apply these things? And again, I got interested in these applications, biological applications. And one of the targets was really to develop this personal handheld diagnostic device, a device the size of this pointer that you can actually use to not only perform basic tests like a glucose test or blood sugar test, but you can actually use it for detecting different markers, protein markers, DNA, RNA markers of various kinds for different applications in your blood, and use it as a personal medical device, personal diagnostic device. So some of the requirements of these things would say basically, if you want to make it low cost and handheld and low power, it really needs to operate in certain ways, and you need to use a certain kind of modality of sensing. The modality we chose was a magnetic modality. So basically, we are using a magnetic sensing modality here, which basically, as an example of that, this is an array we made of these sensor cells. So one of what we see here is basically a magnified view of that, and you can see basically 4 different sensor spots here out of the 64 that you have here in an 8x8 array. And each one of them, well, really 48 out of the 64 of them can be used for detecting different analytes. So using this chip, you can actually look for 48 different targets at the same time in your blood. These can be protein targets or RNA or DNA targets. And this is designed such that the cost structure of this is so that these are so cheap that designed to be one-time use. So once you make these chips, you can actually dispose of them as a part of your test. So, we took this sensor and integrated in the setting, and we made this reusable reader. So this is the reusable reader, and this is our disposable, makeshift disposable cartridge. Of course, it's not going to look like this eventually, but this is basically what we use. And it's a very simple design, which allows you to detect these different targets. And we demonstrated it with 2 different sets of targets. One is a protein target, basically interferon gamma, which is relevant for tuberculosis. And the other one is a DNA assay. And both of them basically that we demonstrated that it works over a broad range. And these plots basically show the sensitivity to these inputs. So, and this opens the door for a lot of other additional kinds of medical diagnostic devices that can be made. And the idea would be to have a handheld device, which basically you can buy a cartridge for a certain kind of disease and put it in and run it and discard, and then have the reader reuse it for a completely different test. And this would be a battery-operated handheld device, which would be low power enough that can operate off of a battery and can transmit the information back to your system. In our design, basically, right now we are using a USB, but this part is a standard part. You can actually do it in different ways. So with that in mind, let me bring it to a conclusion. I think we need to take a holistic approach to what we can do with our technology. We have wonderful technology at our disposal. We are getting closer and closer to a point where anything that's not excluded by laws of physics can be made. The question is that what are the things that we would like to make, and what are the things that we should focus on? Now, we have to really become more creative and versatile. We have to learn more things about more and more to be able to do stuff. And we are really limited to some extent by our imagination and our tools, the tools that we use, and we have to really expand those. Now, we are moving toward a more closely linked world. That's a fact, whether we like it or not. And it brings its own new challenges and opportunities. But we are living in interesting times. Now, in the end, I'd like to thank the people who did the work. This is really, we as professors have the honor and privilege of working with some of the smartest people in the world. And many of these people, these are some of the former and current students who have worked with me in the past. Many of them, I believe 12 of them are already professors at various places, and many of them are running companies. They have started companies, and I'm really proud of their achievements. But we are primarily the cheerleaders for their efforts. And we really have to thank each and every one of them for the efforts that they put in. We also would like to thank our sponsors for the work. And in the end, I'd like to leave you with a thought. Thank you.